This activity gives you another opportunity to derive differential equation models for a circuit. I think one of the frustrating or challenging things for many students when approaching these kinds of problems is they feel that there's lots and lots of different ways to kind of look at the problem or substitute variables. And so in this particular activity, we're looking at a case where we're going to write the same dynamics from two different perspectives. And so in the first case, the differential equation model the variable of the differential equation model, so the thing that has the derivative on it, is the voltage across the capacitor. And the input then, it will be the voltage source V. In the second model, again, exactly the same system describing the same dynamics, but the variable that we'll be interested in is different. And so the variable, or the thing that has the derivative on it in the differential equation, will be the current going through the resistor 1. And so these are two different perspectives of the exact same dynamics. So go ahead and solve this out, press pause, and then we'll look at this in a second. So like in many of the cases, one of the first things you can do if it's not immediately obvious is to redraw the circuit model. So if you have the voltage source, you could draw this as resistor 1. And then this breaks into the capacitor and another resistor. And so this helps to identify that resistor 1 is in series with the parallel branch that includes the capacitor and the second resistor. So this helps identify a little bit better, and I think that's easier to see the branching that happens in the current law. And so if we call I the current that's going across the first resistor, and then I1 and I2 the two branches of the parallel, that means I splits into I1 and I2. And so that's what the Kirchhoff's law, current law, shows here. And for the voltage law, we could choose either of the two loops or both of the two loops. In this case, it turns out we just need one of them. So in this case, we're going to take the loop that goes through the capacitor like this. In this case, the question asked for the voltage across the capacitor. That ends up being the same as the voltage across the resistor. So in the end, it doesn't make a difference which loop we end up taking, because it's both going to be in terms of what we're calling V2, which is just that voltage across either of those parallel branches. So from the current law, we can, so again, in this particular example, we have been asked to find the equations with respect to what we're calling here V2, the voltage across the capacitor. So V2 is now our variable of interest, and so we don't want to get rid of that. That needs to stay. So what we're interested in doing is writing everything else in terms of V2, except for the input, which is V. So V can stay and V2 can stay. Everything else needs to get replaced in terms of dynamic variables. Things like constants like R1 and C and R2, these can also stay because they describe the system. So starting from the current law, we can attempt to start to combine and simplify these to get rid of these other terms. And so again, one of the things to think about is the fact that in this circuit, there is just one dynamic element. So there's one capacitor and no inductors. So that means that there should only be one equation which describes the dynamics of this circuit. So since we have these two equations from the current law and the voltage law, we know that we're going to be combining them. And so you can see that an opportunity to do that is that there is one of the variables we need to get rid of here is I, and it's also here. And so if we solve for this and plug it in here, that helps us eliminate one of our variables. And so then the remaining two things to do is to replace these two variables here. So I1 is the current across the second resistor. And so we can just replace it with V equals IR, and that gives us the V2 that we need. In the case of I2, this current is actually the current across the capacitor, and so its circuit element relationship gives us the derivative of v2. So again, gives us v2 what we need to know. And so now we can substitute that in this position for I, and that will finally get rid of all of the other variables and leave us now here with an equation that is entirely in terms of v2. So all of our terms are v2. This one came here, and this term exploded into both of these terms here. And so now, notice again, the derivative is on v2, so that connects and that agrees with what we set out to do, which is to make v2 this state of this differential equation. And in this case, again, that's being driven by changes, for example, in the input voltage v. And so if we wanted to, we could combine these two things together to get this resulting differential equation. Now, when we solve it with another perspective, so from a different variable being the state, we don't expect to get the same dynamics because that variable may vary different than this voltage does. So let's take a look at that case. In this case, we're interested in deriving differential equations where the state is the current across resistor 1. And again, that's the first element that's in series, and then there's the two elements that are in parallel, R2 and C. So again, we can write down the same current law. Nothing's actually changed about this problem. In this case, it becomes useful to write down both versions of our Kirchhoff law because they end up not being completely redundant in this case. So we'll write one voltage law that goes around this circle and another one that goes around this circle. And so this one describes the voltage across the source, across resistor 1, and then across resistor 2. And so that gives us this Kirchhoff's voltage law. The one that goes through the capacitor yields this relationship. And so we could decide to go ahead and plug in for V2, but remember, in this case, V2 is harder to use because our circuit relationship for the capacitor is that I2 is equal to C times dV2 dt. So it's difficult to use this and substitute in here for V2 using this equation because in this equation, V2 appears as a derivative. So let's hold off on that and wait. So in this case, we're interested in remaining only with the variable I. So we're going to try to get rid of I1, I2, and V2, leaving only the state I and the input V. So our goal is to slowly get rid of these terms. So we can get rid of I2 by substituting in the circuit relationship for the capacitor. That doesn't help us too much in the sense that we've gotten rid of I2, but now we've introduced V2. However, we do have an equation down here that includes V2. And so this is how we could end up using this Kirchhoff's voltage law, is to get rid of this voltage 2. And so right now we can just rewrite it like this. So this is still something we need to remove and rewrite in terms of the current I, which is the state we want. And so that's what we're going to do down here. So we're going to take this expression right here, and we're going to rewrite it in terms of V, which is fine to keep, and I, the current, which is also fine to keep. And so now, to substitute this into here, which is what we're doing here, substitute this into here, we actually need to take the derivative. So now we're getting the fact that V2 dot is equal to V dot minus I dot R1. And so the reason why I have it written down here is the fact that now we're taking this voltage law and taking it and substituting in I1 from this relationship. So I1 gets plugged in here, which leads us to this equation. And then that's where, in this case, in the slide, I'm doing the substitution for V2 dot. And so that's going to be this. So I'm going to substitute this V2 dot into there. And that's what gives me this kind of rather long equation where I've just kind of rearranged some terms. We can rearrange it a little bit more now to specifically gather some terms in terms of, again, I is the state, so we're going to have a derivative. It makes sense that we have a derivative on I. And one of the interesting things, we haven't seen this very much yet, but this is an input. Our input is the voltage V on the source. And in this case, the dynamics that describe the current across the resistor require us to also have information about the derivative of the input. So that means that the evolution of the current I is driven not only by the voltage V, but by its derivative as well. And so that's something that we'll see more and more throughout the course, but it takes more sophisticated systems to see that. So this activity can seem a little complicated, so I recommend going through it a few times to better make yourself feel better about choosing different variables as the output, or as the state. Eventually we're going to call it the output, but the state of the system that we're interested in modeling. So this differential equation is describing how I changes over time. The previous one was how V2 changed over time. So it depends on what we want to see, we can derive the model appropriately.